Thank you for that introduction, Jeff. I'm Jeff Wilson with VSP Technologies, a fluid sealing product supplier based out of Prince George, Virginia. And what we're going to be talking about today is more of a lesson learned, best practices, not so much of a case study, but surrounding different fluid sealing products, gaskets, for highly aggressive chemicals. In this case, it's going to be hydrochloric acid. So before I get too much into my presentation, how much of you guys deal with gaskets? By show of hands. A handful. How many of y'all like working with gaskets? None. Why is that? Is that because it's typically the problematic component?
There seems to be a knowledge transfer issue.
Okay.
Between understanding your hardware, the gasket is the apparent material that you're sealing to.
Okay.
There's a lot of variables, and there doesn't seem to be the right messaging in the industry on what best practice.
Well, perfect. So my presentation is done. This gentleman just summarized everything I'm going to discuss today, and we'll open it up for questions.
Thank you, Jeff.
I'm kidding. So a brief overview of what we're going to talk about today, kind of an introduction, a background of this specific application. We're going to go into a lot of the application details, a gasket recommendation, suggestions, some opportunities that we discovered to learn, final recommendations, and kind of a closing. My goal of this presentation is to keep it impossibly informal. If you have questions during, please raise your hand so I can address them in the moment, so we can minimize any confusion throughout, because I know I'm going to forget some key details, so kind of help keep me honest. I also apologize. I'm a walker when I present, so I'm trying to stay in between the boxes to make sure it's captured, but let's kind of go ahead and hop into it. Who? This specific application was for a customer of ours located in Northern Europe. They've asked us to remain their name out of the presentation, so we've obliged to that, and there's a lot of ambiguity. But what they are doing is they're using hydrochloric acid along with other aggressive chemicals to process their work in project or process materials as well as their final product. So they're using very aggressive chemicals to clean these various products, and they have entire FRP, fiberglass reinforced plastic systems, to kind of convey this. Because as Jose just mentioned, for aggressive chemicals, you're pretty much limited to that fiberglass side of life. Now, one of the unique constraints that we had when we were brought into this process is they were on about 8-week PM cycle, preventive maintenance cycle. So every 8 weeks, they would shut down operation, they would disassemble all the bolted flange connections, change out the gaskets. That seemed kind of problematic. If every 8 weeks you got to shut down production to change out hundreds of connections just to do it again in 8 weeks. So their goal was to find a sealing technology that would help, elongate that process. Maybe it's 16 weeks, maybe it's 10 weeks. Their original goal was more reliability. So how do you think they're going to achieve that? What do you think is going to be a conduit to making sure they have better reliability? Let's find out. So like I said, their specific application or the process section of the plant they wanted us to look at was dealing in 30% hydrochloric acid. So fairly aggressive stuff. They had a lot of fiberglass piping, but also some plastic piping with Teflon lining. So again, pretty common for this industry, right? But what got, a little more, I don't want to say confusing, but challenging, is their temperature was 140 Fahrenheit. They're operating at about a 45 bar. Again, nothing too arduous yet. But that last portion, that available gasket stress, you're looking at about 1,700 PSI, and that's on assembly. That's pretty high. Pretty high. So coming from the metallics world, it's fairly low. From this world, it's fairly high. So how do we balance those out? What do we do to really emphasize how we can seal at these incredibly low loads? Well, one of the most commonly used materials for these applications are elastomers, right? Because they seal well, they're readily available, and typically not too many issues with them. There are also a lot of engineered solutions out there, and this is the current technology they were using, a elastomeric cord material with a PTFE envelope. I'm sure everyone has seen or heard of something like this before, and it can be a very good gasket. One of the big reasons are those stress concentrators that you see there, those ribs on both the PTFE envelope and also that elastomeric core. Because what does that do? Concentrates that stress. That 1700 psi we talked about on the previous slide now goes up, because that is where most of your load is being concentrated. So it's being intensified, which is great, especially when we have a limited available bolt load. So the pros of this gasket are a lot of those things that I just mentioned. But the downside, the Achilles heel, is that core is made of an elastomer. What happens to elastomeric materials after assembly? Before the plant started up, but after assembly, what happens? Say that a little louder. It compresses. What else happens? It relaxes. It squeezes out. That 1700 psi stress we applied to it on assembly is, let's say, about 1,000 prior to startup. Once we get up to temperature, we have cycling, both pressure and thermal. What continues to happen with that material? Decreases. It relaxes. It's no longer mechanically stable, which is fine, as long as you're okay with doing retorques, hot work. But what made this specific application unique is it was a ghost plant. Has anyone ever heard of a ghost plant before? Oh, sweet. So essentially, once they are in operation, once they are running, no one is in the facility. They have cameras, they have everything they need to monitor the process, but no one is actually in the facility because it's hydrochloric acid. So they really don't know if there's a leak until much later in the system. It was not uncommon for them to come back during one of the PMs and find a pool of hydrochloric acid on the floor. Slight problem. So the solution that we're tasked to find is a more mechanically stable gasket, right? Because that's going to be able to solve, hopefully, a lot of these problems. If we can minimize the gasket creep relaxation and maintain that very high gasket stress, like Jeff mentioned, then we're going to be better off to have a mechanically rigid connection and have a solution for this customer. Now, please note that they did try other gaskets before this. This was just the technology they were utilizing when they brought us in. Other elastomers they tried, a few different PTFEs, but none of them got them what they're looking for. So what we had to do is kind of look at all the commercially available products to see what is available to seal at incredibly low loads, handle hydrochloric acid at 30% and 140 Fahrenheit, be mechanically stable, be mechanically rigid. And after scouring everything, we found something that seemed to be a very viable solution. It's an expanded PTFE gasket with a fully encapsulated corrugated metal core. In this case, that corrugated core is made of Hastelloy 276 for better chemical resistance to hydrochloric acid under these conditions. And the reason that it's corrugated, or as the Europeans like to refer to it as undulated, it's a fun word for you, is those corrugations, those peaks are going to act as stress concentrators, just like they did on that ribbed elastomeric envelope gasket. So that way, instead of putting your stress on this entire section of the gasket, you're just focusing it on that insert. So we're able to drive up that stress even more, which is great, right? We have it, now we have a potential viable solution for them that seals at low loads. It's completely compatible with the process and under the given conditions. The issue is going to be price and lead time. Obviously that is something that everyone has to consider. But they were accepting of that. They said that's fine because our goal is higher reliability. And to their credit, when they said that that was their goal, they meant it. They had no problem utilizing or testing this technology. So what we embarked on was a field trial. Obviously, they didn't want to take this unknown to them technology, put it in their system, press the start button and say, let's see how this works. They put in a trial plan. They did that in, I want to say it was early 2020, from flanges everywhere from a DIN 25 all the way up to a DIN 500. For those of you not familiar with European flanges, that's 1 inch all the way up to 20-inch flanges. So everything from small to pretty large. A lot of the common stuff was just like you would expect, that 2 to 3 to 4 inch size range. They started this trial as a 3 to 4 month trial. Following that, very positive results. This is actually one of the gaskets that came out of that trial. And while there is some discoloring on the face of it, it performed fine. The gaskets were disassembled, fully inspected, and it was noted that there was no mechanical wear, unexpected mechanical wear to the gasket. There were no leaks, there were no problems, they didn't have any issues. So what they decided to do in early 21 is outfit their entire operation with this technology. They trialed it on their trial plant, no issues, great results. It's able to last 4 months, no issues. For those of you doing the math, the reliability doubled. We went from 8 weeks to about 16 weeks. So they were very happy with those results. So then we were able to supply the gaskets to these folks. They installed them, and they're done, right? No issues. Do we think that's the case? No. In August 21, we got a call that said, your gaskets leak. Hang on. That's typically the response we get from folks saying, hey, if there's a leak, who do we blame? The gaskets. Just like Jose mentioned earlier, bolted flange connections are very complex variables, right? And it's typically something that not a lot of folks are going to pay attention to because some believe that it is not a engineered connection. So the first thing we say is let's take a step back. Let's get the gaskets that failed back on site so we can evaluate them, but then let's also have some further conversations about what happened. Because let's make sure that these were assembled correctly, right? It wasn't just by Johnny on the spot, bolting it together with an impact, give it a few ugga-duggas and call it a day. To our pleasant surprise, this site paid a high attention to detail on flange assembly. Everyone had to go through and pass a flange assembly course. They also had an inspector following them while they assembled flanges. Maybe redundant, but we could almost rule this out completely as a variable because we knew that these connections were assembled correctly. So what we had to do was really sharpen our pencil. We had to figure out what's going on. Are there system upsets? Is there something irregular going on in these flanges or in this process that could cause this? This is actually one of the gaskets that we pulled out, and you can actually see where the hydrochloric acid had wicked through the expanded PTFE outer layer, got to the insert, that is alloy C276, and ate through it, corroded it. What do you think causes that? Are there any metallurgists in the room? What causes hydrochloric acid to eat away at alloy C276 or hastelloy C276? Well, at the concentration given, they would have to be operating at about 200 Fahrenheit to see this level of corrosion in that time frame. So what we did is we went back to those customers, that end user, and asked them, can you just double check all those variables you gave us? Again, about a year and a half ago, you told us 140 Fahrenheit, 30% concentration of HCl. What do you think they came back to us with? Pardon? They had an upset? Maybe. They were actually operating hotter and at a lower concentration. For those of you who have dealt with hydrochloric acid, at about 20 to 25% concentration, it is more aggressive than it is at 30-35%. They're actually operating somewhere in the neighborhood of 170, 180 Fahrenheit, which, if you check any chemical resistance book, alloy C276 or hastelloy is not recommended. So they were operating hotter, and they were operating at a lower concentration in a more aggressive service. Okay, problem. Some other problems that we uncovered were that the thermal and pressure cycling were a lot more arduous than originally described. Originally, they said they went from about 120 to 140, actually going about 100 to 180 every 8 to 16 hours. They also had an excessive amount of mechanical movement. Now, to quantify that, does everyone know what about 3 feet looks like? You know, it's about yay big, yay long. They had multiple check valves, bolted flange connections moving 3 feet, either side to side, up and down, around. I wish I had the videos that I could show you, but they had excessive movement that caused a lot of mechanical damage to these gaskets, to any gasket, that we were not aware of upon initial assembly, on initial analysis, I should say. Now, do you think that's a problem? Come on, guys. What do you think? Yes, that's a problem. Why is that a problem? Why is excessive mechanical movement going to be a problem with a gasket? Higher stress, we're compressing it, relaxing it, compressing it multiple times, sometimes over a 10, 20-minute period. So we're asking this system to do a lot more. We're asking these gaskets to do a lot more than just seal. They need to maintain their mechanical rigidity during all of that vibration, all of that movement. And unfortunately, that led to stuff like this. Now, before anyone is incredibly worried for the workers here, I just want to note that there were about 250, 300 gaskets supplied for this service. 15 were noted as being a problematic connection, meaning it kind of looked like this. But of those 15, only 5 had this level of damage, and only 3 of them actually leaked. So, not terrible, definitely good, but definitely room for improvement. But it required us, our vendors, our colleagues, to kind of go deep into the playbook of fluid sealing products and see what's available. But what made this even more challenging is not a year and a half ago, we did this same example, the same exercise of what gaskets are going to provide any kind of mechanical rigidity and also be able to handle any kind of thermal pressure, now mechanical cycling. And what it led to was a generation of a new product to the market. We're able to work with a vendor to come up with a product that was actually tested in this service. And while it passed the chemical compatibility portion of it, it required too much stress to actual seal. Again, we're only dealing with somewhere in the neighborhood of 1700 PSI. And the material that we're looking at, which is a silicone carbide filled PTFE, that's that gray portion inside of that gasket, requires somewhere in the neighborhood of 3,500, so double the stress. So we weren't able to use it. But if we fully encapsulate it in that same technology, that expanded PTFE, we're able to hopefully create a better seal based on the conditions given. Now, we did a lot of laboratory testing. We sent it out to third parties to do additional testing. The vendor that was working with us did additional testing. Because again, our goal was, we already went to the drawing board once. Let's make sure the next time that we go back to them, it's with a viable solution that's not going to give them additional headaches. So this is what we ended up recommending. And they put it back in a re-field trial. This time they ran for 6 months, probably because they started noticing issues last time at 6 months. Following this, they saw zero signs of excuse me, leaks, damage to either the gaskets, to the connections, to the system. So they were inclined to add those into their regular system, start replacing out all of those previous gaskets with this technology. And what you can see here is we have some Fujifilm we used a regular gasket on top of it, and you can see where it is darker, where it's intensified, is how much stress we're able to concentrate. Where on the gasket itself, we're only putting about 1,500 PSI, and that's what's available to us from those bolts. But on the insert, we're somewhere in the 3,600 PSI range. And that's not including those stress concentrators on the peaks. That's only the insert itself. Again, this was a unique solution for a very unique problem. When these were supplied back in 22, about mid to late 2022, they were installed, and we have not heard anything back from them besides the gaskets are not leaking. I very well could receive a call tomorrow saying that they are, but considering we are about 2 years in, I'd say that that's a success. We were able to take them from, again, a PM cycle of 6 to 8 weeks. Now we're pushing 2 years. And the more important part, at least from their vantage point, is the system, the facility no longer has to operate as a ghost plant. People can go in hazmat suits, of course, but look at these connections if they think that there's an upset, an issue, which is great because previously that was unheard of. They could not do that. So they do have the ability to send trained personnel in while operating to look at everything, inspect everything, so they can be on the front end of any issues that might occur. So a few of the lessons learned we had here kind of goes without saying, and I'm sure everyone here does it multiple times a day with a customer, is when you're dealing with any kind of system, specifically non-metallic, be double darn sure that they know their numbers. This is the design conditions of your system, not the operating conditions. Because those design conditions are typically higher temperature, higher concentration, higher pressure. So that way you're dealing for the worst case scenario. So you have that kind of in the back of your mind to make sure that what we're recommending is not going to cause them an additional headache. Another refreshing one was, since this was Europe and we're used to dealing with folks in the States, their level of detail for flange assembly was extremely refreshing. Here we've worked with folks that said, hey, I'm assembling a flange and I was, let's say, not working at the facility 3 weeks ago, maybe flipping burgers. So that, I'm not joking, but not joking. Someone has actually said that. But their attention to detail on something as complex as flange assembly is critical. They knew that. They were accepting of that. They knew what they needed to do to make it happen. But then also knowing what technologies are available given the unique solutions that you have. You know, in some cases, most cases even, you can probably get away with just a regular sheet cut elastomeric material, and it's going to be fine because you're not asking that technology, that gasket, to do anything more than hold back a few PSI of aggressive chemical. But when it is extremely aggressive, there's a heavy thermal component and mechanical component, that there are other technologies out there to help you achieve a seal, but more importantly, maintain a seal for the life of that connection and increase the reliability of that either connection or that site.